Hello friends, subscribers and new viewers of this channel, and welcome to FPGA tutorials. In this tutorial, we provide an introduction to the always statement in the Verilog programming language, and we explain how to implement several examples that demonstrate how to use the always statement in Verilog and Vivado. The always statement is a very important statement in the Verilog programming language. It can be used to implement both combinatorial and sequential circuits and designs. It enables you to execute a Verilog block when an event occurs. The event is user-defined and it is specified by the sensitivity list. For example, by using the always statement, we can execute a block on every rising edge of a pulse clock variable. Here, the sensitivity is a rising edge of a clock. We can also specify even logical statements in the always block. But before we start with the explanations, here is the copyright notice. This video lesson developed code files and documents should not be copied, redistributed, or posted on public or private websites, public or private code repositories, or social media platforms. This lesson and all the provided study materials are strictly for personal use. Without the permission of the author, this lesson and the provided material should not be used for commercial purposes and for training of engineers working in companies. This lesson and the provided material should not be used as lecture materials on online learning platforms and in the official university courses without the permission of the author. This lesson and the provided material should not be used to train an AI algorithm or a large language model. Okay, let's start with explanations. The always statement has a number of different forms. For brevity of this tutorial, we cannot cover all the cases and all different forms. We will cover the basic cases that will help you to understand the always statement and the main logic behind it. The basic form of the always statement is given over here. We write always, then we write at, and then in parentheses we specify the sensitivity list. Then we start the block with begin and we end the block with end, and inside we have a series of statements. The expression denoted by sensitivity list defines an event that triggers the execution of block of statements between begin and end. That is, over here, once the conditions specified in the sensitivity list are satisfied, this block will be executed. For example, if the sensitivity list contains a list of signals that are usually separated by commas or by or, the statements in the always block are executed sequentially whenever any signal in the sensitivity list changes, and we will explain this in more details in the sequel. Consider this example. Over here, A and B are binary signals. That is, they can take the values 0 or 1. And here's how the always statement looks like. We say always at A, B. Then over here, we have two statements. The first statement implements the AND gate, and the second statement implements the OR gate. These two statements are executed whenever any of the signals A or B changes. For example, let us assume that A was 0 and B was 0. Then, suddenly A goes to 1. Since A is changed, this sensitivity list is triggered and the always statement will execute the block within begin and end. That is, these two statements will be executed. Similarly, now if A goes back to 0, then again these two statements will be executed. And the same thing applies to B. That is, whenever any of the signals A or B changes, this block will be triggered and executed. In the earlier versions of Verilog, that is before Verilog 2001, OR keyword is used instead of comma in the sensitivity list. That is, In older code files, you will find statements that look like this. You will see always, then at, then over here, instead of comma, you will see or. That is, you will see A or B. Let us talk now about the order of execution. Over here, it's very important to keep in mind that if the statements, such as these two statements, are written outside of the always block, then they are executed concurrently, or better to say, at the same time. This is very important. However, in the always block, the statements with the operator equality, such as these two statements, are executed sequentially, that is, one after another. These statements are actually called the blocking statements, since the previous statement blocks the subsequent statement. That is, in this case, this statement, C is equal A and B, is executed. Then, after this statement is executed, the second statement, that is, D is equal to A or B, is executed. That is, the statement C is equal to A and B blocks the statement D is equal A or B. And that's why these statements are called the blocking statement. Namely, the reason is that the statements are executed sequentially, one after another one, and that's why one statement has to be executed, and until this statement is not completed, the next statement will not be executed. Here's another example that explains the use of the blocking statement. This example is very similar to the previous example with one significant difference. Over here, instead of A, I introduced C. So we have a statement C is equal and A and B, and the second statement D is equal C or B. So what's happening over here? Since this is a blocking statement, first C will be determined. Then this determined value of C will be used in the second statement. Besides the blocking assignments and the blocking statements, we also have non-blocking assignments and non-blocking statements. Non-blocking assignments are executed at the same time. For non-blocking assignments, instead of the equality operator, we use this operator over here. And here's another example. This example contains non-blocking assignments, and you can see a difference between this example and the previous example. The difference is in this assignment over here. Now, let us see the consequence of this. For example, let us assume that A is 1 and B is 1, and that the previous value of C is equal to 0. The right-hand sides of the both statements are actually executed at the same time. From the first statements, we will have that C becomes 1. This is because both A and B are 1, and this is the AND gate. Now, this value will not be used in this second statement. This is because both of the statements are executed at the same time. And when the second statement is executed, the previous value of C will be used. That is, C is over here 0, and B is 1, and 0 and 1 produces 0. Consequently, once this block is executed, C is 1 and D is 0. And keep in mind this. Another important thing to keep in mind when using the always statements is to always declare the variables on the left-hand side of the operator's equality and this operator as reg data types. The reg data type can store information. Consequently, to make this example functional, you need to declare that both D and C are registers. That is, their data type is reg. This is very important, and this applies to both equality and this non-blocking operator. Then, since Verilog 2001, we can use the symbol star in the sensitivity list. This will trigger the always block for any input signal changes. Let us consider this example. Over here, A and B are declared as inputs and D and E are declared as outputs. Then, since we are using C and D in our always statement, then we need to declare them as registers. And you see what's happening over here. We are saying always at star. This will automatically recognize what are the inputs and it will automatically create a sensitivity list. In this case, whenever A or B change, this block will be triggered. And we achieve that by using the star symbol. The benefit of using the star is that sometimes people might forget the signals that should be in the sensitivity list. Over here, you let Verilog to automatically determine. And this is a sword with two edges. If you don't know what you're doing, this star can create an issue. However, if you're perfectly confident and you have properly defined the inputs, this statement will work perfectly. Then, in the always statement, we can also have more control when we want to trigger the block. For example, we can trigger on the positive or the negative edge of a signal. For that purpose, we use this keyword pos edge and neg edge. For example, over here, I define a module that will execute this always block on the positive edge of the clock. In this particular example, a clock is a train of pulses, and whenever the rising edge of clock arrives, this block will be triggered. We can also use the always statement without the sensitivity list. Here's one example. In this particular case, we are actually creating an infinite loop. What's happening inside? This statement has a delay of 50 time units. The time units are defined at the beginning of our code and that they can be nanoseconds or picoseconds. In this particular case, let's assume that the unit is a nanosecond. Consequently, over here we have a delay of 50 nanoseconds. And this statement will create a shifting of clock variable between 0 and 1, and delay will be 50 seconds. This will create a train of pulses. Namely, clock value will stay constant for 50 nanoseconds, then it will change the value. For example, if it was 1, it will become 0, and then after 50 seconds, it will be assigned back to clock. And this creates a train of pulses between 0 and 1. We can always write something like this. For example, in this case, again, we don't have the sensitivity list. However, in this statement, we are setting, for example, A to 0, and over here we are executing this block whenever the clock changes from 0 to 1. That is, we are triggering the block on every positive edge of clock. And that's it. This was a brief introduction to the always statement. In the sequel, we will implement two examples that explain how to use the always statement in practice. In the sequel, we will implement these two examples that demonstrate how to use the always statement in the Vivado programming environment. Here's the first example. In the first example, we will implement AND and OR gates, and we will embed them in the always statement. And here's the second example. In the second example, we need to define a clock that will be used to trigger several assignments. The assignments should be executed on the rising edge of a clock. So let's start with the first example. First of all, we need to start Vivado. So click on Start and search for Vivado. In this video tutorial, I'm using Vivado 2024.1. However, you can use any other version of Vivado. So let's wait until Vivado loads. And we actually don't need to use a real FPGA board. So let's create a project. Click here, click on Next. Then let's use these default settings. Click on Next, click on Next. And over here, we actually don't need a board. However, I will still select the board I like and that I often use in my tutorials. This is Nexus A7100T. Here it is. Click on Next and click on Finish. Okay. The first step is to create our source. Consequently, locate this menu Sources, then click on Design Sources and click here. Then make sure that the second option is selected, Add or Create Design Sources. Click on Next. Over here, click on Create File, and let's call this file as test_module. Click on OK, click on Finish, and click OK, and click on Yes. In these video tutorials, I assume that you know very little about Vivado and about FPGA programming. Consequently, I will explain the main things and I will spend more time explaining the basic concepts. Now, where is our source? If you click here and if you expand, you will see the test module. Double click on the test module and over here we need to enter our code. Let's erase these comments until the time scale and let's start with coding. The first step is to define and to declare the input parameters as well as the output parameters. We do it like this. Over here, I'll type input 1, input 2. Input 1 and input 2 are the input parameters, or better to say input variables or input signals, and then I need to define output signals. So here's my output 1 and then I will have output 2. Okay. Next, we need to say to Verilog that inputs are input 1 and input 2 and that outputs are output 1 and output 2. That is, we need to declare inputs and outputs. Let's do it over here. Declare inputs and outputs. This is how you write comments. So let's type input and let's say input 1, comma input 2. These are the inputs. Don't forget to add the semicolon. And then we need to say outputs. Outputs are output 1 and output 2. Good. Now, let's analyze our logics. Over here, we see that output 1 and output 2 are on the left-hand side of the assignment operator. Consequently, they need to be declared as registered, since they need to store information. So let's do it over here. We need to declare output 1 and output 2 as reg. So let's type reg output 1, comma output 2. And that's it. Good. Next, we can implement our always block. So let's type always, and then over here let's specify add, and let's specify the sensitivity list. In our case, the sensitivity list is trigger the always block whenever either input 1 or input 2 change, or they change at the same time. We do it like this. Then we need to say begin, and over here we need to say end. And then we need to type output 1 is simply input 1 and input 2. This is how we implement the AND gate. Similarly, we need to say output 2 is input 1 or, this is how we implement the OR gate, input 2. And that's it. This is our module. Let's again repeat what we did. Over here, we specified the parameters, then we declared what are inputs and outputs signals. Here we need to declare output 1 and output 2 as reg. This is because they are on the left-hand side inside of the always block, and here's our always block. Note over here that output 1 and output 2 are actually blocking statements. That is, output 1 is a blocking statement, and first this statement will be executed, and then the second statement will be executed. However, in this case, since we don't have delays, more or less they will be instantaneously be executed. So the next step is to simulate this module. For that purpose, we need to create a test bench and simulation. To do that, locate over here the simulation folder, then do the right click and click on Add Sources. Over here, select Add or Create Simulation Sources, click on Next, then click on Create File, and let's call the file as module test bench. Okay, and click on OK. And click on Finish, and click on OK, and click on Yes. And wait for a while. Now, if you expand this subfolder over here, you will see our test bench module. So click over here to open the file. Now, erase all the comments until the time scale, and over here you can erase the parentheses since we don't need them. Okay, the first step is to declare our variables. So what are the variables? Since this is a test bench module, for inputs we need to use registers. Consequently, we need to type reg, then we need to say input 1, and over here I will use the letter T to denote that this input is actually an input from this test bench, and I will do the same thing for the second input. Next, we need to declare the outputs. In this case, the outputs will be vires. So again, we will type output 1 T and output 2 T, and then semicolon. Next, we need to declare our unit under test. That is, we need to connect these test bench inputs and outputs with the inputs and outputs inside of our module. So let's learn how to do that. First of all, we need to go back to the test module and we need to copy the name of the module. And we need to paste it over here. Then we need to give the name to our unit under test. I will call it UUT. And then over here, in parentheses, we need to connect the blocks, or better to say, to connect the signals. We do it like this. This input over here, input 1T, let's copy its name. Let's type dot and then input 1, and let's repeat. This input is actually related to input 1T. Okay, then let's add comma. Then again, let's do this. We need input 2 from our module, so let's type over here dot input 2. Then we need to connect it with input 2T signal. Then let's continue, and let's do the same thing for output. So over here we will need output 1 dot output 1, and this is actually in the test bench output 1T. And let's do the same thing for the output 2. So let's just copy this without comma, output 2, and over here output 2T, and that's it. Now the inputs and outputs are connected between test module and our test bench. And over here we need to specify what we are going to do in our simulation. First of all, we need to say initial begin. And after that, we need to initialize the values for our inputs. That is, at the beginning, input 1T will be 0, and input 2T will also be 0. Okay, then let's introduce a delay of 100 units In our case, we can see that the unit is 1 nanoseconds, and consequently over here we will wait for 100 nanoseconds. And then we will switch input 1 and input 2. What we need to do? We need to sweep through the values of. So let's put it like this, sweep through the values which are, let's put it like this. First of all, we have for the input 1 and input 2, 0, 0. Then we have 0, 1. Then we have 1, 0. And then we have 1, 1. That is, we are basically creating a truth table where we are going from one row to another row of the truth table, starting from 0, 0. That's the first thing over here. Then 0, 1, 1, 0, 1, 1, etc. And over here, we will simply switch the values. So let's switch first of all to this. Then let's again wait for 100 units. Then, oops, here I made an error. Here should be input 2 should be 1. Then we need to switch to this. Then again we need to copy this over here. And finally we need to switch to 1, 1. And over here we are sweeping through the values. There is a more elegant way to do this, and you can do this in a for loop or by using the repeat statement, and you can do it in a single line. I actually did it in one of my previous tutorials, whose link will be given in the description below. Okay, so that's it. Let's make sure that over here we end initial begin with end, and over here a good idea is to make this code to be nicer by selecting this and simply by pressing tab. Then everything over here will be under initial begin and it will be nicely aligned. Okay, that's it. Let's save this test bench and let's simulate the test bench. To simulate this test bench, we need to click over here on simulation sources, then right click, and in fact we don't need to do that. This might be a more difficult way. The easiest way to simulate is to simply click over here on run simulation and click on run behavioral simulation. And let's see what's happening over here. Here you need to be patient and bang, here it is. And let's analyze our simulation, move this. Over here you need to zoom out. There are several ways to do that. You can simply press over here, or you can press Control, hold Control, and use the middle mouse button to move this part over here. So let's see what's happening over here. Let me now zoom in a little bit and let's analyze what's happening. Okay, this is the initial case. Both input 1 and input 2, you can see them over here, were 0. Then after 100 nanoseconds, we switch input 2 to 1, and we can immediately see that output 2, which is actually the output, let me expand this, which is actually the output of the OR gate, becomes 1. However, the value of output 1 is 0, and this is because output 1 is the output of the AND gate. And then we go further. Over here we switch to 1, 0, and we can see that output 1 is 0, that is our AND gate is 0, and our OR gate is 1. And then finally we switch to 1, 1 for the inputs, and we can see that the output of the AND gate becomes 1, and the output of the OR gate stays 1. And that's it. Simple as that. And after that, you can see that the simulation just runs until the end value over here, and that's it. This is because we are not changing any values, and the last values stay as they are. Okay, so this was the simulation of the first circuit. We learned how to simulate everything. If you go back again over here to this test module, you can connect all the dots and you can see that this always statement is being executed on every change of either input 1 or input 2. Let's continue with the second. Next, we explain how to implement the second example. In the second example, we need to define a clock that will be used to trigger several assignments. The assignments should be executed on the rising edge of a clock. So let's go back to Vivado and let's implement this example. Click on File, click on Project, New, then click on Next, click on Next, click on Next. Let's select the board. In fact, the board really doesn't matter. However, I like to select this board, click on Next, and click on Finished. And click on Yes over here to close the previously opened project. The first step, as always, is to create our module. For that purpose, click on Design Sources, click here on plus, make sure that the second option is selected, click on Next, click on Create File. I will call the file as Test Module, and let's click on OK, and let's click on Finish, and click on OK, and Yes. Now expand Design Sources folder and double click on Test Modules. Then let's enlarge this window. Let's erase all the comments over here and let's start with coding. First of all, our test module will have several arguments or parameters. I'm going to have output 1, output 2, and then I'm going to have clock. The clock will be the input and output 1 and output 2 will be the outputs. So let's declare clock as the input and let's declare the outputs to be output 1 and output 2. Okay, that's it. However, since the output 1 and output 2 will be on the left-hand side of the assignments in the always statement, we need to additionally declare them as regs, that is as registers. So let's type reg and let's type output 1, comma, output 2. Now, since they are registers and in my simulation I need to specify their initial values, I need to type this. I need to type initial to declare the initial block. Then I need to type over here begin and end. And inside of this block I need to specify the values for output 1 and output 2. Let me type output 1 to be 0 initial and output 2 to be 0 initial. Of course, you don't need to do this. There are several ways to specify the initial values, however I like this approach. And here's an additional comment. In practice, this block over here is very difficult to synthesize and it might be challenging even to implement this. However, for the purpose of simulation, let's specify the initial values like this. Okay, next we need to define our always statement. So what do we want to do? Over here we have clock as the input. Good. We want to trigger the always block on every rising edge or positive edge of our clock. Consequently, we need to type always at, oops, I made an error here, at, then we need to type pos edge, where pos edge stands for positive edge, and over here we need to specify the clock name. The clock name is simply clock. And that's it. Then inside we need to have begin, and over here we need to have end. So what are we doing inside? Let's play around. For example, let's type this. Output 2 will be equal to not output 1. Interesting. So if initially output 1 is 0, not output 1 will become 1 and it will be stored in output 2. Then output 2 will become 1. However, let's change the previous value of output 1. So let's type this. Output 1 is now equal to the new value of output 2. So let's again go and analyze this. Output 1 is 0. This thing becomes 1, is assigned and stored in output 2. So output 2 becomes 1, and then since output 2 is 1, output 1 will become 1, and we change the value of output 1. Now in the next iteration, output 1 will be 1. Over here we will switch it back to 0, and then output 2 will be 0, and this is how we will create a series of pulses. Okay, simple as that. Let's save this module. Let's make sure that there are no syntax errors or some other errors. Often in Vivado you will see a syntax error, or even this nice environment will be able to recognize a compilation error, and you will see a red line below the text. However, we don't see it over here, which means most likely everything is fine. The next step is to define our test bench file. So let's do it. Let's change the size of this window. Let's locate simulation sources, do the right click, click on add sources, make sure that this third option is selected, click on next. Let's create a file and let's call it module_test, test bench, and let's click on OK. Let's click on finish and OK, and yes. Here wait for a while, then expand this folder and double click on a test bench file to open it. Here it is. Now again, let's erase the comments. Over here we don't need the parentheses. And let's start. First of all, the clock variable has to be a register over here. So let's type register clock, and let's use T again to specify that this clock is inside of our simulation. Over here we need to be very careful. Output 1T and output 2T should not be declared as regs. Instead, they need to be declared as simple signals or wires. So let's type this wire, and then let's type output 1T and output 2T. Next, we need to define our unit under test, and we need to connect our test module with our test bench. To do that, we need to go to the test module file. We need to copy the name of the test module. We need to go over here. We need to paste this name, and let's call the unit under test simply as UUT, and over here in parentheses let's specify the connections. Don't forget the semicolon over here. So let's type. We need to connect output 1 with output 1T. Consequently, dot output 1, this is our output 1 from our module, should be connected with output 1T. And we define this connection like this. Let's do the same thing for the output 2. Again, let's change the numbers, and now output 2 from our test module is connected with output 2T inside of our simulation. And finally, let's do the same thing with the clock. That is, this is the signal from our module, is connected to clock T inside of our test bench. That's it. Let's save this file and let's continue. The next step is to design our simulation. To start our simulation, we need to type initial begin, and over here we need to end. The first step, as always, is to initialize the value of clock. So let's specify clock T is 0 and add the semicolon. Next, let's add a delay of 200 units. Let's go all the way up, and over here you can see that the unit is 1 nanosecond. Consequently, over here we have 200 nanoseconds. Good. Then let's repeat a piece of code. To do that, you can either use a for loop or you can use repeat. I will use repeat, and over here I will start with begin, and over here I will end this block with end. And inside I'm going to periodically switch the value of clock. The period will be 100 nanoseconds. Consequently, this is how delay is introduced. And I need to type clock t is equal to not clock t and semicolon. Let's analyze what's written over here. This statement will keep the previous value of clock t for 100 nanoseconds. Then it's going to change clock t either to 0 or 1. That's why you have this not over here, or shifting or changing the value. And it's going to assign the new value to clock t. This will create a train of pulses for clock t starting from 0. That's it, simple as that. Now, when a rising edge or the positive edge of clock t is detected, our module is going to execute this block over here. And let's simulate this. Make sure over here that you save, scroll all the way up, and here it's very important that you don't see any red line below your variables. Since I don't see any red line, I can proceed to simulation. So click on Run Simulation and click on Run Behavioral Simulation, and let's see what's happening. Here it is. Now let's move this here. Let's enlarge this window. Let's zoom out, press Ctrl, and use the middle mouse button. That is the roller to zoom out. And let's see what's happening over here. Magic happens. Let me now expand this and let's see. Okay, here it is. Let me zoom in a little bit better and let's see and analyze what's happening. Over here, we can see that the clock is 0 for the initial 200 nanoseconds. That is this part over here correspond to this time over here and this behavior of clock. Now we trigger the clock and we change the value of clock. Clock goes from 0 to 1 and you can see over here that it's being changed. Very interesting. Then the value will be kept constant, right? However, now over here we can see that output 1 changed and output 2 changed. Initially both output 1 and output 2 were 0. They're being changed since over here a positive edge of the clock is detected, and then we are inverting the values and we are storing them in the corresponding values. So if output 1 was 0, output 2 becomes 1, and output 1 becomes output 2, which will again become 1, since these are the blocking statements. And this is how this code goes. Then nothing happens on the negative edge or the falling edge of our clock. Then again, nothing happens until over here we trigger the positive edge. Then again, the always statement is triggered, and we continue like that, and we propagate further. Over here you can see that this code is simulated for approximately 1 million nanoseconds. Or no, sorry, this is 100 nanoseconds. You can proceed further. If you click here, then you'll have further simulation, and you can again simulate, and you can go on and on and on like this. And this will be simulated in the future and propagated until 20 repetitions of this loop over here. Okay, that's all for today, and thanks for